Hey everyone, welcome to my YouTube channel. So, the purpose of me creating this channel is to teach you guys different concepts, different maths and physics concepts, and to really help you guys get an understanding behind these concepts and not just how to do problems. So, my first video is going to be on kinetic and potential energy. So, let's get started. So, kinetic energy is the energy of motion, and it's defined as 1/2 mv squared. So we are around Christmas time, so I'll draw a little sleigh. So we have Santa's sleigh here. Just pretend that's a reindeer, right? If this reindeer is pulling the sleigh, and the sleigh is moving at a velocity v, then that means that the sleigh has kinetic energy. Next, we have potential energy. And potential energy can come in a few different forms. The form that we're going to go over in this video is gravitational potential energy. So we'll notate potential energy with the G for gravitation. And what this symbolizes is if you have someone, let's say standing on a cliff. Let's say you have Santa standing on a cliff, and there's some water below him. And Santa wants to take a dive into the water, right? With Santa, let's give him a little beard. There we go. So, if we have Santa standing over here, and he wants to take a dive into the water, then because of this height that he's standing at, he has gravitational potential energy. Essentially, potential energy is energy due to height in terms of gravitation, and the height is based off a reference point. So in this case, we have a reference point as the ocean. So that's our reference point. Potential energy, gravitational, is equal to mgh, with m being the mass of Santa, g being the gravitational constant, which is 9.8, and h, of course, being the height. So let's go over a couple concepts. Alright, I do realize that my previous scene was a bit to the left, so I'll try and draw more in the middle here. But energy is neither destroyed nor created, meaning that it must be transferred. What that means is that the sum of your initial kinetic energy and your initial potential energy must equal the sum of your final kinetic energy and your final potential energy. Remember, energy is neither created nor destroyed, meaning that it can only be transferred. So, let's take a look at the Santa example. We have Santa standing over here. I'll just draw him as a regular guy for now. Have some water down here. So, Santa over here is currently standing at a height h. We'll call this height h. And he weighs m. So currently he is not moving, right? Before he jumps, he's not moving. So initially what we have is we just have potential energy. And that's because Santa hasn't jumped yet. Santa's still standing there, meaning that Santa has all the energy left to gain. He's not moving, therefore he does not have energy in the form of kinetic energy. So we'll say potential energy, gravitational, equals. And now let's say in our final scenario for our right-hand side of the equation, Santa jumps, right? Santa's diving into the water. He's taking a little splash. Santa's jumping. In this case, he has a velocity going downward. He still has his mass. And yeah, that's all the info we need for now. So, as Santa's jumping, when he reaches the bottom, when he's finally at 0 height, he will have only kinetic energy, right? And obviously, as he goes deeper into the water, he'll slow down and everything. But this is right as he's hitting 0 height. He'll have all his kinetic energy. If we're looking at some point in the middle, he would have potential and kinetic energy, but we won't worry about that for now. What this means is that our initial mg height initial, equals our 1/2 m, our final velocity, squared. And from this, we can figure out Santa's final velocity, figure out heights, and solve the system to find, whatever we might need to find his mass, to find maybe the energy of the system, whatever we might need to find. All right, so we have a problem here. Let's get this text out of the screen. All right, so we have a problem here. We have a 2 kilogram object that's moving at a speed of 5 miles per hour. We're trying to find its kinetic energy, so that's our first point here. And we're finding the gravitational potential energy if it rises to a height of 3 meters. So let's start with part A, the easier of the two parts in my opinion. So we have our 2 kg object, kgs, and let's just say it's moving this way at a speed of 5 meters per second. How do we find its kinetic energy? Well, we go to the kinetic energy calculation, which is 1/2 mv squared, which will give us 1/2 mass, which is 2, v, which is 5 squared, and once we calculate all of that, we should get 25 joules. So that would be our final answer to that problem. Let's get rid of this on our screen. And let's go to the second part of the problem, which says if it rises to a height of 3 meters, finds gravitational potential energy. So in this case, we have an object, right? It's a 2 kilogram object. And let's just say, for our purposes, it went up a ramp. So it went up a ramp here. Still the same 2 kilogram object, but its height is 3 meters, right? So we're looking at this final scenario right here. You can ignore this initial part. This is just what we started with in part A. But right now we're in the ramp scenario, right? What would our potential energy be? Well, potential energy is defined as mgh, which is just the mass, which is 2 kilograms, times the gravitational constant, which is 9.8, times our height, which is 3 meters. And if we were to calculate that, we get 58.8 joules. And that would be our answer. All right. So we're now on problem 2, which says that ball is dropped from rest from a height of 10 meters. What speed is the ball just before hitting the ground? And what happens to its potential energy? So we're at a height of 10 meters, so I'll draw, a little cliff here. And the ball standing at the edge of the cliff, getting ready to jump down. And the cliff is 10 meters high, so we'll put a little notation there that says 10 meters. And ask what its speed is right before hitting the ground. Right? So let's just draw out a ground here. It's asking for the speed of the ball when it just is about to touch the ground. There's still a tiny bit of space there. It hasn't hit the ground yet, therefore it has not bounced back up yet or has not stopped yet. Whatever the scenario might be, it is right about to hit the ground. What is its speed? Speed, in other words, would be, just velocity in the scenario. The absolute value of it, rather. But we can just say velocity for now. To calculate this, what we need to do is use our initial, so our PEI plus KEI. Our initial equals our final formula, right? Conservation of energy. Well, in this scenario, if you take a look, you see that at the top, the ball's not moving, meaning that it only has potential energy. If a ball is not moving, it has no kinetic energy. At the bottom, the ball is already at its 0 point, meaning that it has no potential energy, no gravitational potential energy. Therefore, only has kinetic energy. So now our revised equation would be PE equals KE. So if we set this up, I'll do it up here. We get mgh equals 1/2 mv squared. You can see that mass cancels on both sides. The mass of the ball doesn't change. So the mass stays constant, therefore it can divide out on both sides and cancel. So now we have gh equals 1/2 v squared. What a lot of people like to do is solve for v in terms of variables and then get its value. But what I actually like to do is plug in first. So what I'll do is plug in 9.8 for the g and 10 for h, and then set that equal to 1/2 v squared. Let's go down here. This will give us 98 equals 1/2 v squared. Then we multiply by 2 on both sides, and we get 196 equals v squared. And then square root of 196 is 14. So we get v equals 14 meters per second, which means that our speed is 14 meters per second, meaning that's our answer. Alright, let's look at part B of the question. What happened to its potential energy? Well, when we were solving our question, our potential energy all got converted to kinetic energy. So for this problem, our potential energy gets fully converted to kinetic energy, and that's part B of the problem. So now let's look at an AP level problem. Alright, so this problem says a 1.5 kg block is released from rest at the top of a frictionless ramp that is 5 meters high. At the bottom, it moves onto a rough horizontal surface where the coefficient of friction is 0.30. Find the speed of the block at the bottom of the ramp and how far does the block slide before coming to a rest. So the very first thing I like doing is just drawing a picture. So quick diagram of our scenario. We have a ramp here, and then a rough surface here. Here's our 1.5 kg block. 0.5 kg. Our ramp is 5 meters high, so we'll draw that in. Let me actually make sure this is on screen. We'll go with this, and then we'll just say 5 meters down here. It says at the bottom moves onto a rough horizontal surface with coefficient of friction of 0.30. So we'll do that. Okay, so that looks like we drew everything. Find the speed of the block at the bottom of the ramp. Well, in this case, we can again use our initial energy equals final energy, or equals kinetic energy. And that's because at the top, the block isn't moving initially. Before we release it, the block is completely still, meaning it only has potential energy, gravitational, to begin with. At the bottom, it is only moving. It's at its 0 point. So it has no more potential energy, gravitational. So it only has kinetic energy. Now we can set this up to say something like mgh equals 1/2 mv squared. Again, masses cancel. So now we have gh equals 1/2 v squared. So we'll get 9.8 times 5 equals 1/2 v squared. And when we solve for v, I won't go through it. Essentially, you would just multiply this, multiply 2 on each side, and then square root both sides. And our v, we should get 9.9 meters per second. Or around 9.9 meters per second. Okay, Now let's go to our part of the problem that says how far does the block slide before coming to rest. So I'll actually erase this part A just so we make some room. Let's erase part of this too. Alright, now that we have some room. How far does the block slide? Well, one thing we know is that the force of friction is our coefficient of friction times our normal force, which on a flat surface, such as this one, so let's just say our block makes it here. On a flat surface, the normal force is equal to mg, or gravitational force, because of equal and opposite forces. So what this really equals is force of friction equals mu mg. Again, our gravitational force is mg. And we know that work equals force times the distance over which the force is applied. Our force in this case is our frictional force pointing that way. So we'll put a little subscript F there by our force. So this would simplify down to mu mg times our distance. Okay, let's also define another aspect of kinetic energy. So work is defined as change in kinetic energy. What this means is 1/2 mv final squared, and then I'll just put it down here, minus 1/2 mv initial squared equals work. In our problem, we have work equals, this little expression down here, which equals 1/2 mv final squared minus 1/2 mv initial squared. In our problem, our block is coming to rest. That means that our final velocity is 0, canceling out this entire expression. Now, we know that 1/2 mvi squared equals mu mgd. So let me just rewrite everything here so that you can see that clearly. So I'll delete that. We'll say mu mgd equals 1/2 mvi squared. Should be a negative as well. So we have this expression. And we can solve for d here. D equals, we'll cancel out mass on both sides. We'll say, we know mu, we know gravitational constant, so we can say negative 1/2 vi squared over, let's see, it looks like mu g. And we're looking for the distance here, meaning that would just be the absolute value of our displacement, so to say. When we solve this, we get our displacement equals 1/2, because you want to take out the negative sign here to get the absolute value. Of course, if the final value would be a negative value, anyways, you would just remove the negative sign, get the absolute value. That would be your answer. But you get distance equals 1/2 times, what did we say our initial velocity was? Well, we said that our velocity when we just hit the bottom of the ramp was 9.9 meters per second, I believe. So we'll get 9.9 as our initial velocity for this system. Now let me make this very clear. if we're looking at this ramp system right here, our initial velocity would be 0, and our final velocity would be 9.9. But because we're looking at just the rough surface here, our initial velocity is 9.9, which is the final velocity of our ramp system, and our final velocity is 0. So I hope that's clear. If that's not clear, leave a comment down below. I'll try and get back to you. We have that over 2 times our coefficient, which is 0.30 times 9.8. And you type all that into a calculator, and I'm just gonna do that real fast. And you get 16.7 meters. Alright, so I hope you enjoyed my very first video on this channel. If you do have any questions, leave a comment down below. I'll be sure to get back to them. A couple big takeaways to end this video is that when forces are conservative, meaning when there's no outside forces acting upon a system, PE initial equals KE final, and PE initial plus KE initial always equals PE final plus KE final. Now, this is conservative forces, and this is always. Friction, of course, breaks mechanical energy conservation. So if we did add friction here, and we didn't account for it, this wouldn't be true. But as long as we do account for frictional energy, this can be true. And often on the AP exam, your problems will simplify to energy and work. These two concepts are heavily related, so be sure to look out for one if you see the other, and vice versa. So, if you do have any questions, as I mentioned, leave them in the comments below. If you have any new video suggestions, I'm open to that as well. I hope I've made this clear for you, and I hope that you enjoy your holidays. Have a good one.